Swayam Prabha. Digital India. Educated India.
In this lecture, I am going to show you something that is very interesting. See, until now, what we have looked at for the structures or members subjected to axial load, that if you have the member and if you are pulling it or pushing it from the ends, when we look at cross sections which are perpendicular to the longitudinal axis, we see that each of these elements are actually subjected to some kind of normal stresses, right? And consequent to that, you have normal strains, essentially expansion or contraction. What we are going to see here in this particular lecture is that if for the same structure, if you're looking at it slightly differently, if you're looking at it at different angles, you will see that in addition to these normal stresses which we had looked at, we also start to develop some amount of shear stresses, right? And this is particularly becomes detrimental for structures which are weak in shear, right? So now going back to our topic, we are going to look at stresses on inclined sections. So again, reiterating what we had looked at before, if we have this structure and if I'm pulling it or if I'm pushing it, we had looked at these vertical sections. Wherever we have, remember those cuts which we did while we're looking at the uniform axial or non-uniform axial load, were all perpendicular to this longitudinal section, and essentially the stresses you had were simply the sigma x. Now what we are going to look at is that if in this structure you are cutting it at a different angle or a different plane, then what are the kind of stresses that emerge, right? So this is what we have seen until now, right? So if we had a particular structure over here, right, where we have taken an imaginary plane section Mn over here, right? Because of this one, we have this stresses which is the sigma x, straightforward. We have a nicely uniform stress sigma x which is acting at the end wherever you are cutting this cross section. And remember that delta equals to PL divided by AE, where it happens at every individual section, that gives you the total deformation, right? Now, if I look at this in 2D, this is how it looks like. Again, now within this, if I take another, tiny bit of a small element over here, say a small element like this, if I blow this out of proportion, it, looks something like this, where we have a sigma x p over a, and this is the same figure over here, which is looking in the two dimensions, right? And this is what we have seen, right? So now I am posing you with a different problem. I am posing you with the problem that for the same structure, instead of taking this Mn perpendicular to this longitudinal axis, if I take it at a particular angle, at a particular slope, right, then what happens to the stresses on this particular face? If I take this instead of Mn, which is vertically down, if I take this PQ, which is at an angle, then what happens to these stresses which occur at this particular cross section over here, right? Here we have seen we have this uniform sigma x equals to P over A, only normal stresses and no shear stresses develop in this particular section, right? So if we are looking into this one over here, it looks something like this. See, eventually, even if you're cutting this section over here, right, if we have the leftward force P over here, I'm going to have a balancing force P on this end as well. I have to maintain equilibrium, because that plane is not going anywhere. At the end, that plane remains within that particular structure. It only displaces slightly, so the force must balance out, right? So again, if I look at this in this 2D, and you have maybe this is the stress distribution, and the resultant of this stress times the area of cross section over here equals to this particular force P over here, what we get. So now you are probably wondering that now we have this particular force P. Now what are the kinds of stresses which emanate, or we generate in this particular surface PQ over here? Now some of you may have guessed it already. So simply what probably we have to do is take this particular force P and maybe resolve it into two components, maybe a normal component which is normal to this face PQ, right? We have this face PQ, so it is normal to this face PQ, and a shear component V, right? Now remember, the normal acts, of course, from the name itself, normal to that particular face, and the shear component acts at a particular angle. Now just to demonstrate that, if this is my cross section at which I'm going to, shear is acting like this, right? So it's on the surface. It is like brushing against the surface, the tangential kind of an action which it does, which we know shear to do. right? So now if we look at it again, so what we have over here, that again reiterating and looking at the same structure, we have this load P and we have cut this particular section over here, which is PQ, right? And this is my normal, which makes an angle of theta over here, right? So correspondingly, as you can tell, that this particular angle over here becomes 90 degrees minus theta, right? Or pi over 2 minus theta over here, right? So now that we have this one, and as we saw that in the previous slide, that or the that we have this particular force which eventually leads to this particular force P over here, which has split it into this N, the normal component, which again acts about this particular the normal to that plane at an angle of theta, and we have the shear component V. Now, so as you can tell that if this particular angle is theta, my N becomes equals to P of cosine of theta, right? And V becomes P sine of theta. Simple. Now let's come back to this figure over here. So here, as you see that what I have essentially done, that because of this normal force which is acting along that outward normal from that plane PQ, I have a normal stress. So this stress over here is normal to this particular face PQ over here, right? Now, so how do I write this particular stress? If I have to write it, this particular stress is nothing but, I'm going to call this as sigma theta is going to be equals to my normal force N divided by this cross-sectional area, the inclined cross-sectional area. And what is the inclined cross-sectional area? If this angle was theta over here, it is going to be A divided by cosine of theta. Now remember, what was A? A was nothing but this cross-sectional area. This cross-sectional area is A, right? So if I am cutting that plane at a particular angle theta, then the inclined plane has this particular area of cross-section, that is A divided by the cosine of theta. So here my sigma theta, where sigma theta is this particular stress, becomes equals to N divided by A1, right? So if I have to sort of simplify this or maybe expand this slightly more, what I get is that my sigma theta is going to be, I know that N is P cosine of theta, right? So I have P and A1 is A divided by cosine of theta, so it is going to be P by A, one of the cosine goes up, cosine square of theta, right? Because N is P cosine of theta and A1 is A divided by cosine of theta, that cosine goes up, so it becomes P divided by A cosine square of theta, right? Now remember, what is P divided by A? P is nothing but this particular force which is acting over here, and A is the area of cross section which is perpendicular to the longitudinal axis, which is essentially this one. If I had the P and if I had the A, I had P divided by A is nothing but this particular quantity which is sigma x, right? So the equation which I just derived over here, I can replace P divided by A by sigma x over here. So if I have to sort of simplify this even slightly bit further, so I have that my sigma of theta is equals to P divided by A, I am replacing with sigma x, right? Also, what I am doing, I am going to pull a denominator 2 over here to make it 2 cosine square theta, and I know 2 cosine square theta is 1 plus cosine of 2 theta, right? So P divided by A gets replaced by sigma x, right? And I divide by 2, so I have to multiply by 2 in the numerator. So that means that becomes 2 cosine square of theta, which I sort of expand this into 1 plus cosine of 2 theta, right? Now let's look at this particular terminology or this particular formula which we just derived for sigma theta. Remember, sigma theta is this particular stress which is acting normal to this inclined cross section, right? Now let's see that at theta equals to 0, now we are going to vary the angle and check, and let's take one particular angle theta equals to 0. So at say theta equals to 0, what becomes to sigma theta? Sigma theta reaches its maximum value. Why? Because I know the maximum value of cosine 2 theta is 1. So cosine of 0 is 1. So at theta equals to 0, sigma theta becomes sigma max, right? So sigma max, what I can write is that sigma max becomes equals to sigma x by 2, 1 plus 1. So it becomes equals to sigma x, right? Now, and what happens, and where does this happen? That's the question. Not what, where does this happen? It happens at the point where, as I said, theta equals to 0. So what does theta equals to 0 mean? Theta equals to 0 means that this normal, if you make this theta equals to 0, it is essentially the horizontal line, and this is exactly what we had seen, that when we have this horizontal line over here, suppose the outward normal is along this horizontal line, then sigma x is p divided by a, so your sigma theta at theta equals to 0 becomes equals to sigma x, and this is what we just derived. So at theta equals to 0, sigma max becomes equals to sigma x over here, right? Okay, so the maximum normal stress, remember, whenever you're cutting these inclined planes, the maximum normal stress happens when theta equals to 0. That is when you are, when your outward normal points exactly towards this particular force P, or in other words, the section that you have cut is exactly vertical, or in this case exactly perpendicular to this longitudinal axis, right? Now let's look at this guy over here. Here we know that this particular force which is acting is V, which generates this particular stress, the shear stress tau over here. So how can we write tau of theta? So tau, maybe let me change my color, tau of theta becomes equals to, same, tau is also a stress, so it is the force divided by the cross sectional area, so that is V divided by A1, right? So now if I have to again write this a bit more further, what I essentially get is that tau of theta, V, remember, is p sine of theta, right? And I have a1 below, so it is going to be, and if I replace a1 by a divided by cosine of theta, so it becomes p divided by a sine theta cosine of theta. Simple, right? Again, as I did before, if I take p divided by a and replace that by sigma x, and I pull a 2 in the denominator, I will have 2 sine theta cos theta in the numerator, right, which is sine of 2 theta. So if I have to simplify this or expand this as I did previously, what I will get is that my tau of theta becomes equals to sigma x over 2 sine of 2 theta, right? So now that I have this formula for tau of theta, right, as you can tell that if this, along which section does this become maximum, right? The maximum value of sine is 1, so that means 2 theta must be equals to pi over 2, right? So that means your theta becomes what? Theta becomes pi over 4. So that is at 45-degree angle. So here it is 0 degree. So if I have at theta equals to 45 degrees, right, my tau max becomes equal to sigma x over 2 times sine of 90, that is 1, becomes equals to sigma x over 2, right? So for these two quantities, that sigma theta, we have seen that sigma theta becomes maximum at theta equals to 0 over here. Now at theta equals to 0, what is the value of tau of theta? Let's put theta equals to 0 over here. You will see tau of theta becomes equals to 0, which is obvious because when I was taking this particular section over here, that at theta equals to 0, I did not have any shear on this particular face, I only had a normal stress, right? So again, so at theta equals to 0, sigma max equals to sigma x, and tau at theta equals to 0 degrees is equals to 0. Similarly, if I take a look at the bottom one over here, right, at theta equals to at 45 degree, tau theta becomes equals to tau max equals to sigma x over 2, but does the normal stress vanish? Let's see. we have this generic formula for the sigma theta over here. So what happens to sigma theta at theta equals to 45 degrees? So if I have to write that sigma theta at theta equals to 45 degrees becomes equals to what? If I put 45 degrees over here, then it becomes cosine of 90, which becomes 0. So sigma of theta equals to 45 degree becomes equals to sigma x over 2. So this is important, this particular relationship that you just saw, right? That if I am taking a cut at an angle of 45 degrees, for example, here, if suppose this theta over here, if this was 45 degrees over here, then this sigma theta will become equal to sigma x over 2, right? And the tau of theta will also become sigma x over 2. So, and this has implications. We will see in a minute, this has some serious implications, right? So this is one of the important relationships that we saw. And the other important relationship is, this one over here, which we saw, that at theta equals to 0, which is essentially you're cutting the plane which is normal to the longitudinal axis over here, you have no shear stresses, you only have normal stresses, right? Now, so what we saw that within the same structure, if I am cutting the section which is perpendicular to the longitudinal axis, I only have sigma x, no tau. And if I am cutting this at a 45 degree angle, then that face that I will have, that face will have an outward pointing normal sigma x, which is sigma x over 2, and a tau which is going to be sigma x over 2 as well. And all of this, remember, is happening within the same structure. It just depends on how you are looking at it. So just to reiterate, if I take this bar, or which I was showing, maybe this sponge or this bar of a particular material, right? Now let's take a look here. You have two elements, which is A and B, right? Now if you take a look at element A over here, which is nothing but this one, right? Element A, you see, has been taken such that this particular face, right, the outward normal makes an angle of theta equals to 0 with the horizontal, right? And for that we have seen that the forces which we are going to have are simply going to be sigma x and sigma x, no tau, right? Whereas in contrast, if you take a look at element B, which is cut at an angle of 45 degree, especially this particular face that you see over here, let me maybe mark this face. So this N makes an angle of theta equals to pi over 4, that is 45 degrees. So essentially this particular face, right? What do we see? In this particular face, I have a sigma x over 2 and I have a shear force, right? And the value of the shear force is going to be sigma x over 2. Now here I am only showing you for this particular, cut section. So if I take similar sections about this and about this, about the other faces, if I take sections about, this face or about this face or about this face at different, where the normal makes at different angles, you can put it back in the same formulas which we derived before. You can put it back essentially in these formulas over here, and you will see that what you will get is that you will end up with these kinds of stresses, sigma x over 2, and this is going to be your sigma x, the outward normal will be sigma x over 2, and the tau will be sigma x over 2 as well, which we just saw. Whenever you take it as 45 degree, you end up with these stresses, the normal stresses and the shear stresses, which are essentially, so this is my element B which I'm looking at, right? So we end up with this sigma x's and the tau also is sigma x over 2 equal, but the nature is completely opposite. One of them is a normal and one of them is a shear, right? Okay. Now that we have looked at it, now why did we learn this? What's the necessity for this, right? The necessity for this is that you have materials which are extremely strong in either tension or compression, but beyond a particular point they are weak in shear. So if you take that particular material and if you're thinking that I am going to stretch it beyond any imaginable limit, since because it is say very strong in tension or very strong in compression, you cannot assume that the material will not fail. It fails. If it is weak in shear, if it is strong in tension or compression, it will survive the pulling or the pushing force. but if it is weak in shear, it will fail along a different particular angle, right? Let's look at a particular video to make this concept clear, that what are the types of materials. One of the classic examples of such a material is wood. So the video which we are going to look at is a block of wood which is pressed vertically down, and you will start to see that the failure planes beyond a particular point happens at a 45-degree angle. So let's take a look at that video now. So what you see here is a block of wood which is being pressed from the top as well as the bottom, right? So as I will play this video, you will see that initially, due to this compressive forces from the top and the bottom, some cracks will start to develop in the middle, but look at the failure pattern, at what angle it eventually fails. So let's take a look at this video, right? So you see, because of the normal forces, you're starting to have a little bit of cracks in between, but after a while, you see the failure pattern starts to emerge along this 45-degree angle on both the sides. Why? Because wood is substantially weak in shear, right? So essentially, after a while, the shear failure starts to happen at those 45-degree angles, right? You have similar other kind of members, you have similar other kinds of materials as well, which are quite strong in tension and quite strong in compression, as long as you're looking at the cross section which is perpendicular to the longitudinal axis. But these elements can also be weak in shear, and what happens in such cases is that you start to have failure along that 45-degree plane. So overall, I hope that you have enjoyed this particular topic while we looked at the normal stresses and different cases. For example, the case in which have a uniform axial load along the longitudinal axis. We have the non-uniform axial load, for example, in the same member, the axial load is different at the different points. You have members which are varying in cross section, and in the end, what we looked at was for the structure, instead of traditionally, quote unquote, traditionally looking at sections which are perpendicular to the longitudinal axis, if you're looking at sections which are inclined at different angles to the longitudinal axis, in addition to the normal stress sigma x, we are also going to have some amount of shear stresses as well.